Okay. Let's just get it started. Thank you everyone for coming here. So today we are going to have Professor Nobuo Hinohara give a seminar on nuclear pairing and related phenomena in nuclear dynamics. He's from, let me make sure I pronounce it right, University of Tsukuba, right? Tsukuba. He's currently an assistant professor at the University of Tsukuba and actually also a adjunct professor here at Every. His research is broad, including nuclear structures, galactic phenomena, in particular DFT density functional theories. And he's also interested in, for example, neutrino double decay or double decay calculations and all those. He got his PhD in 2008 from Kyoto University, and then spent a few years in Yukawa Institute of Physics, and then Riken Nishina Center, right? And then 2011, and between 2011 and 2014, he's working as a postdoc at University of North Carolina, soon with John Nobuo. But somehow he's also at the same time visiting University of Tennessee at Knoxville, right? And then after that, he's a visitor at NSCR between 2014 and 2016. But at 2014, he already started at the University of Tsukuba. Okay, let's welcome the speaker.
Thank you very much. So I'm thank you very much for this introduction. In this talk,
But that actually sometimes requires you to put it very, very, yeah, because we very
thank you. Okay, so this I'm going to show some of our recent projects in nuclear pairing, and so this area is international serial of my project. So I don't have any some very detailed explanation of everything, but I will just show some.
There's a strange noise. There is somebody. Let's go to is there another microphone? Seems like the connection's kind of it is kind of.
Okay, so now there's a problem. So it's
no problem. Yeah, you can move it up. Yeah.
Thank you. But I start from some yeah. So this is the objective user web page, and so there are several questions that if we want to clarify, there are from infrastructure and nuclear astrophysics and from some of the related to some fundamental physics. There are interesting questions like how are nuclei made and organized, and what is the nature of this nuclear matter, where do nuclei elements come from, and what combination of neutrons and protons can form about nucleus. And also there are questions related to neutrinos. Neutrinos their own antiparticles. And in many of the questions, actually nuclear pairing correlation plays an important role. it may not be central rule, but it plays an important role. So my talk is basically related to these questions of every science. And I think this is the most important thing in every science, where the nuclear elements come from. And so there's a process that is a process that these heavy elements are basically created in some explosive event like supernova or neutron submersion. So there's a process path in the neutron bit side. This is a composed of the neutron capture process and beta decay. And also, if very heavy elements are created, there are fissions or fission rates and fission parameter distributions are also very important role for understanding the whole process. And the important thing is that our process is taking place in a very neutron-rich system, and this is basically beyond the current and maybe a future experimental measurement. So we need theoretical prediction to understand the whole process. So that's the reason why we theory. And so there are many nuclear structure theory, like ab initio type theory, and there's a shell model configuration reduction, and we also have density function theory. And currently, the density function theory is the only microscopic theory that can compute from all unstable nuclei, including all these process nuclei. And we can even compute the structure of the neutron star from this approach. So we are going to use this nuclear density function theory. I will not explain the detail of this theory, but this is basically based on this Hartree-Fock type equation for obtaining the nuclear ground state. So this is an eigenvalue problem. The eigenvalue problem is usually a linear problem, but it's a non-linear eigenvalue problem because the matrix segment depends on the eigenvectors. So we solve this eigenvalue problem for a given matrix segment, and from the eigenvector u and v that they are called as quasiparticle functions, we can construct the densities. And the matrix segment, the eigenvalue problem depends on this thing. So we have to solve this eigenvalue problem iteratively until we get self-consistent convergence. So this is what we do in the nuclear calculation, the ground state. And we are sometimes interested in the excited state when we discuss dynamics. And for this purpose, we use quasiparticle random phase approximation. And this is another eigenvalue problem of a very large dimension. So dimension is up to 1 million, but this is not a iterative problem. In a nuclear DFT, the input of the theory is basically this energy density functional. It's a functional density or pair density. So we need this quantity to solve this equation. And energy density functional should be related to some nuclear interaction, nuclear force, but currently it is basically determined phenomenologically. So the parameters in the energy density functions are basically limited for this expanded data. And EDF is composed of kinetic energy, particle for energy, carrying energy, and Coulomb. And carrying energy is here, and this is one of the important component in the energy density function. So, and nuclear pairing is basically some part of the nuclear interaction that give additional value in energy if there's a pair of nucleons, if their interaction is occurring. And this is about the pair of fermions. And fermions have to be antisymmetric if we exchange index of the two fermions. And nucleons are fermions, but it has spin and electric units of freedom. This means we can decompose the nucleon to nucleon wave function in terms of spatial part, spin part, and isospin part. And in total, it should be antisymmetric for the exchange of two nucleons. This means spatial part and spin part and isospin part should be antisymmetric. So one of the components should be antisymmetric, or all the components should be antisymmetric. That's a possible combination for different pairs. And there is a nuclei force created to each channel. That is called a singlet, even parity-odd, even singlet odd. And this notation was basically based on the either basic channel is spin-singlet or spin-triplet. And also this whether this is a parity-even or parity-odd. So they are coming from this property of the spin spatial part. And as the spin part is automatically determined if we fix this two. When we discuss nuclear pairing, it is basically singlet even channel. So it's a spin-singlet, spin up down pair for isospin triplet. So this will contain right particle pairing, like neutron pairing or proton-proton. Yeah, this also has a neutron-proton. Yeah. And in this talk, I would like to discuss not only this singlet even pairing, but I'll discuss a little bit about triplet pairing, which we usually don't consider in the nuclear structure, but yeah, discussion that some of the triplet or channel like triplet into have a superfluidity in the interior of the cell. And I'll discuss a little bit about this channel in the finite system. And I'll also discuss this triplet in channel that is as isospin and symmetry. So this is a neutron-proton pair, but spin triplet. So spin 1, isospin 0 pair. There's a large impact on beta decay and double beta decay half-life of this channel. I don't know anything about this singlet odd channel, so if you know anything about this channel, let us discuss later. And this is some information for the professional EFT people, but they are corresponding, they are testing EFT. So basically, yeah, by looking at this pair density, you can see information about the nuclear pairing in this channel. And before discussing a little bit more about the pairing, I have to comment about the difference between correlation and condensation. So correlation is basically if there's some contribution in the Hamiltonian, we say there's a correlation. So when we discuss about pairing correlation, means we have some pairing in the Hamiltonian. But this does not mean that we have a impact from this correlation to the EFT ground state. So especially the DFT is an approximation to the full many body theory. Small weak correlation may not have any impact on the ground state. This situation is written this type of figure. So these are energy as a function of some other parameter that represent correlation of the system. And if the correlation is weak, the EFT solution is at the correlation. This means there's no correlation in the ground state. And if we increase the amount of the correlation, the curvature of this potential is going to be so. But still, the solution is at the origin. So there is no contribution to the ground state wave function. But if we discuss some excited state, that's basically the vibration of this ground state, this correlation will play some. And this will be discussed in the level of QRP. But if this correlation is very strong, there will be a condensation. This will be a significant contribution to the ground state. So if we are soft on the potential energy surface, at some point, the minimum will move from the origin to somewhere here. Here we have a finite value for the order. So we have a true correlation in the ground, near the ground state. So this is the condensation. In this case, we have a impact on the ground state and also excited states. This is again a vibration, but this correlation has some impact. And this process of having this condensation is basically understood in terms of this containers. And to discuss this a little bit more, I'd like to start from some discussion about deformation. Maybe this is more familiar to everybody. We discuss, we want to start what is the shape of the nucleus. In the theory, we can do a ground state calculation to see what is the ground state deformation. So here's, for example, of the quadruple deformation. You can see some of the nucleus are spherical, some of the nucleus are already deformed. In experiment, there's several observables. One of the observables that have the direct connection with the deformation is the D from 2 plus state, Z plus state. But we can also look at the lower energy spectrum. And especially the 2 plus and 4 plus states are important. If the system is spherical, especially we can regard this 2 plus as a quadruple vibrational excitation, and 4 plus state as a 2-phonon state, quadruple vibration. So in this case, the energy is expressed in terms of the number of the phonons. So the ratio of the 4 plus energy and 2 plus energy is 2 in the limit of the spherical system. But if the system is deformed, we can regard these 2 plus and 4 plus states as a rotational excitation. So energy is now proportional to angular momentum I times I plus 1. The energy ratio is n divided by 3. So by looking at the lower energy spectrum, we can see whether this is nucleus is spherical or. Here's the experimental value of this alpha ratio. We can clearly see at magic numbers like 82, 126, 82. We have very small alpha ratio. Basically, this green part is and we go to this open shell system. This is value is close to 3. So they are basically formed. So we can say which nucleus is deformed or which nucleus is spherical, like Then how about the pairing? So when we discuss pairing in the theory, we can calculate pairing energy or pairing. And we can see which nucleus is in the normal phase, which one is the superconducting phase. At the magic numbers, especially neutron pairing completely vanishes, but we have some finite value in the ocean region. But experimental corresponding quantities of the mass traveling, that is basically some binding energy systematics. And if you compare the binding energy of even system and odd system, there will be some systematic deviation because in the odd particle number, there will be less binding because there are some of the pairing deviations. So we can extract this. Here this is some experimental observable pairing, and here's the experimental value neutron of the stability and proton of the stability. But you can see that this is not a very good indicator. We cannot see any clear normal things. That was seen in this chemical calculation. We can see some region around 126 where we have smaller of the stability, but we cannot see much in the line system, for example. This is some but it's not big compared to here. But if you look at the dynamics, again, there's some pattern. So if the system is in an normal phase type, like this case, the excitation to the neighboring nucleus is related to the pairing vibration. So again, you have some phonons, and this is excitation to the 2-particle more system and 4-particle more system. And the energy difference is basically again 2 because this is the 1-phonon excitation, this is the 2-phonon excitation. But if there is a condensation and system change from this picture to this picture, we will have a new degree of unfold, also mode, and that is for the pairing rotation in the case of nuclear pairing. And we can see this also mode by looking at the binding energy systematics of the system. So this is the pairing rotational energy calculated at the experimental value for T isotope as a function of neutron number. And you can see some parabola behavior. So now pairing excitation energy for this rotational picture about this vibration. So there's a difference whether depending on whether this the system is in a normal phase or superconducting phase. And actually, there's a new observable. So we have a pairing rotation, and we can set this the reference state as a function of the neutron or particle number. Then we will have this moment of inertia of the pairing rotation as a function of the particle number, and this will be a pairing related experimental observable. And this is quantities related to the inverse of shell gap. So we can compute this inertia for the pairing rotation from the binding energy of every even nuclei. And this is written in terms of the two-neutron separation energy difference. And here's some comparison between experimental data and theoretical calculations for the pairing rotation and inertia for the plate and calcium isotopes. You can see a good argument. You can even see that certain type of induction can be produced better than the others. So we have a very good sensitivity structure or property that pairing by the You can also see a clear phase transition much more high. So compared to the old standard, this will be a observable for the pairing. Of course, we can extend this discussion not only to the single shell, but we can compute this inertia for all mass event. We can see here some normal phase. Here, because this is basically the inverse of the shell gap. And we have had extended this discussion. So in the case of nuclear shape and rotation, we introduce this R-4 ratio. We can introduce the same quantity for the pairing. So now we can somehow extract some pair excitation energy for the 2 plus minus 2 neighboring system or plus minus 4 neighboring system. Then by taking this ratio, we can say that if it is 2, system is in the normal phase. But if it is 4, it's pair rotation, so system is in the superconducting phase. In the case of pairing, we can have this ratio to the neutron decreasing ratio or neutron increasing ratio. So we have 2 sets of the quantities, but in any case, we can see that most of these systems show R4 to ratio around 4. This means most of the off-the-shelf systems are in the pairing rotation. So we have a pair condensation ground state. And this is very visible in the experimental data. And there are some lines that correspond to R4 ratio equal to 2 with a paired vibration. This is happening at closed shell system that is n equal to 26. We can see some in the experimental. This is basically equivalent to some ratio of the 2 neutron shell gap at the neighboring nucleus. So if this 2 neutron shell gap is the same for the series of the atoms, the ratio of R4 to 4. But if it changes very much, then this will deviate. And so this is the indicator for the nuclear pairing. And we can discuss the same one. Again, you have you can see that in the most cases the R population is 4. You can see some 28, 58 regions that have a relatively smaller R population, but this is a little larger than neutron case because we have Coulomb interaction. And Coulomb interaction is proportional to this square and this is basically pairing rotation. So on the direct contribution of Coulomb interaction is the case of proton. So by using this information, we can identify which nucleus is really identify this particle. So we can define, for example, some deviation from this alpha to value equals 4. And here we brought the nucleus that shows this deviation is smaller than 0.6. So we allow some 10% deviation from alpha to 4. Then we can say this 200 nuclei neutron superconducting. It's another 200 nuclei are proton. So this kind of information is, I think, very important when we discuss pairing property further, like we can get functionals. We can basically use this information. And we can investigate, for example, some of the nuclei used in the unidepth optimization. So in unidepth optimization, some of the nuclei are used to fit the pairing part of the functional. So these nuclei are the ordering subgroup of neutrons are used, and for these cases, the proton ordering subgroup are used for the functional optimization. But if we calculate this deviation, it is actually large in some cases. So this fermion to 52 is about 1.7 of this deviation. So this is actually very far from the alpha to the ratio 4. But in the case of unidepth, in unidepth too, they added several more new nuclei, and they show a relatively small alpha deviation from alpha to 4. So in unidepth too, I think this situation is slightly good, but we can use this kind of information for choose when we choose the nuclei use for the NPI. Okay, I like to talk on topic, but you can see the pairing. And this is about the alpha particle. So alpha particle is important in freedom, and in the system we have alpha plus 1. But when we go to the heavier system, we usually do not discuss much about the alpha particles. But still we have alpha decay, a very heavy system. And there we are alpha knockout reaction to see how alpha particles are the ground state. So there's a TP alpha cross-section measurement for arsenic oxide velocity. So they measure this cross-section to the transition to the ground state in isospin as a function of particle number. They got this cross-section. So the cross-section is decreasing as a function of neutron number. And this is explained in terms of the effective model that includes alpha particle explicitly. So in this paper by Stefan Bell, he calculated some alpha particle length in the nuclear surface. So it's a very small value, but he got some alpha particle distribution as a function of this neutron number. This is increasing if we go to the neutron side. So this is the integrated value. So number of alpha particles in the surface is decreasing, and this trend basically explains knockout cross-section. So this kind of expanded will be able to capture how many alpha particles are in the surface region. But we try to understand this in terms of the standard nuclear theory. So we define some local alpha numerical strength. So we have initial nucleus and try to remove alpha particles that are coordinate R. And this is about the energy of the final nucleus. And this is just a complex conjugate. So these are strengths. So in the alpha particle at position R, and this specifies the energy of the final. But we made some approximation, but now the alpha particle is just a point line. So it should be a Gaussian. Let's take alpha particle. In this case, actually, we have 2 neutrons and 2 protons, and the total strength, if this is integrated in terms of this final state energy, this is just alpha delta alpha. So this is showing that how many alpha particles are there at coordinate R. This quantity is product of neutron part and proton part. If there's no neutron proton mixing in it. Then this neutron part, for example, is neutron data, and neutron. So totally quantity. So we can decompose it into one body densities and pairing density. And this is related to some spin density, so it should be 0. And so there will be some enhancement population of the neutron pairing. And in the surface region, actually, this enhancement it's a quantity divided by this the first term. So it should be 1 if there's no contribution from the second or third, but if there's a contribution some term, then yes. So this is pairing from the neutron pairing contribution. And we can try we try to evaluate this contribution to the cross section. So we evaluate this function of the ground state to the final ground state using this simple operator DAT. And this is the matrix element square with some masking function because the reaction is basically taking place at the surface. And this is a structure calculation. We try to mimic some region on the reaction. So it should be the more realistic reaction theory, but this is a structure calculation. Then we can basically explain this experimental frame by this simple calculation. And this is basically coming from neutron pairing. So here's a neutron pairing as a function of the number. And this is maximum around here, and it is decreasing the neutron number. And this trend is basically coming here. So both the alpha particle model and the neutron pairing can explain this experimental trend, but if we can measure the LiDAR system, the pairing, but number of the alpha particle increase because in approach Z, so there will be some deviation. You can see which effect is important. Okay, and I'd like to talk a little bit about the inertial function of nuclear fission. So nuclear fission is a very important process in the end of the alpha process path. And there will be some spontaneous fission. So and its half-life is very important. And the half-life of the spontaneous fission is calculated from the action. And action is some integration over the fission path. And there is in the WKB semi-classical approximation, there is a inertial as a function of the path and potential in the surface. So we have this kind of potential in the surface as a function of definition, and fission is taking place by this quantum domain. And we also need to evaluate this inertia. And this is, I think, one of the first calculations. We evaluate this inertia from theoretical basis theory. So we have some effect from the dynamics. So there is the effect from digital reduction. And if we compare this, is some parallel branching inertia that is completely known from theoretical. We have some enhancement, some region. And this is actually associated with this pairing. So this is a pairing as a function of the deformation. And when this pairing change around, we have very enhancement. So pairing have a large impact on this addition inertial value. And actually, this is too large. Imbalance reaction by this inertia is 20. This means we have many orders of magnitude of difference in the factor. But this is still a one-dimensional calculation of 240 and not very realistic. So as a future plan, we are now planning to extend this calculation to dimension. So this symmetric asymmetric coordinate and try to evaluate this inertial function, the function to coordinate this QRT types. So we will see more about how we can contribute to this efficient dynamics. Okay, then next I'd like to talk a little bit about triplet-odd. Yeah, triplet-odd is
Can I ask?
Yes.
So in this, so what are the units for effective mass for the inertia?
Oh, effective mass is actually how it's not a liquid mass, it's a mass for the effective dynamics. It showed how the nucleus system can easily change shape for configurations.
Yeah, but what, I don't know what is MEP inverse? What is this?
Oh, so it's effective mass in terms of this zero. So we have this in for this mass. So yeah, it's kind of inertia for changing zero value to a system.
But shouldn't it come out as momentum simply, PDS, and it's actually
So it would be
EVN S is distance, right?
this is the actually the issue part. So it stands Q0 in this case. But in the real mission probably be more complicated. So then I will talk about triplet pairing. So it's a parity-odd like even pairing. So it should be spin-triplet and also isospin. So it's a spin one right particle like pairing. And actually, there's a tendency probability recombinant matter system. There's a A phase and B phase. Like maybe this is a famous figure phase 7 for the tendency. And there are two defined superfluid phase. And these are others in terms of even system. And we have many phases because there are more order particle in the channel. In the singlet is in the standard pairing, we have just one order parameter, that's a complex quantity. But in the case of triplet P, there's a spin contribution. It's a squared. We have spin and also there's a momentum contribution. It's a period. So it's a 3 times 3. It is 3 times 3 is 3 now. 3 from momentum and 3 from spin. So there's a 9 order particles total. So that's the reason why we have various superfluid phase in period. And actually, this A phase is correspond to certain combination of this finite order particle. B phase is from this diagram. In the case of nuclear DFT, the singlet is especially the same single complex pair is that expectation value of pair annihilation spin up and spin down. In the case of triplet E, triplet node, there's a so-called spin kind tensor appearance. So it's a non-local pair density is spin, and we have a derivative for two coordinates. So there's a contribution from the momentum, and there's a spin contribution. So this is 3 times 3 tensor one total. So we can expect some variety of different superconducting phase correlated to channel. But if we impose a spherical symmetry, it's all about that with this one, so it's much easier. So in this case, we have just seen spin orbit pair density. And this looks very similar to the normal pair density, but we have some extra contribution from here, and this is equivalent to the phase. So there's a contribution from spin orbit.
So when you say spherical symmetry, you mean that all the triplet P waves have the same strength? So that's for P. What do you I'm not sure if I understand.
Oh,
so the 3P0, 3P1, 3P2, all are the same.
Yes, but we impose a spherical symmetry to the given state. When we have only one. So we have just one channel. We have only radius, radial part of the so this is one. So spin orbit plays are important here. So here's a condensation for Cauchy isotope. So this is a singlet pair condensation, a function of little number. This is triplet pair condensation. Upper previous when we use a spin-singlet pair induction. So this is a standard pair induction. And this is a very exotic pair induction. We don't have any singlet pair, but we have triplet pair induction. And this red curves are calculation without symbolic induction. So in this case, we don't have any 28 matching numbers, so we have condensation between any 28. But if we increase symbolic, we will see this 28 matching. And if we look at this triplet pair condensation, we don't have any condensation if we don't have spin orbit, but this spin orbit we are going to have some condensation, even if we don't have any interaction in the spin triplet channel. And this is because of this LS contribution to the pairs. So triplet pair condensation is usually induced by spin interaction, even if we don't have interaction in the and this is a kind of exotic pairing, but in a standard scan interaction, this component is present. For example, there's a SKP interaction. It is repulsive, but there's a contribution. And in a spherical nucleus, this corresponds to parity-even. And this is basically repulsive nuclear force, but in some of these scan interaction with tensor part, like SL5 plus T, this channel is applied. So we may have some contribution from this channel to the conversation. So we are planning to extend this discussion to include some actual information. So this will include not only P1 but also P2. This is important to include but we need minimum observable forms for example. Yeah. And we mean that the pairing rotation momentum inertia will be a good candidate to see some effect of yeah. Okay, the last part I'd like to discuss a little bit about proton pairing, and so it's about the triplet even channel. So it's a spin triplet, isospin singlet, and neutron-proton part. And the important question is how to determine the interaction strength for this channel, because there will be no condensation in the ground state, neutron-proton isoscalar. Yeah, this means the as a function of neutron-proton pair amplitude or the parameter stability in the origin. So we see some effect on the excited states, QRPA, but there is no ground state contribution. But we are working on including this neutron-proton pairing in the ground state. These collaborators, but I will not talk about this thing. So basically, neutron-proton, isoscalar neutron-proton pairing is important in the excited states. So one is the data decay half-life. This will have a rising process discussion. And there will be also a correlation to neutrino-limiting and neutrino-less double data decay half-lives. And so this neutrino-less double data decay will confirm the binary property. It's silent. So this is another important physics. And I have a panel that will discuss a little bit about how correlation is any both system. Yeah, and for the beta decay, actually there's already a systematic discussion, and the isoscalar pairing is globally limited to beta decay half-life by keeping massive checking using the QRK. But QRK is actually just an approximation to the theory. So there it is missing some of the important correlations. The QRK includes coupling to two quasiparticle state that is called damping. But it is missing coupling to more complex computation like multiple quasiparticle state. And this corresponds to a square this. This also has some coupling to components. So this will give us some escape. And so in this collaboration, we mean that the people in North Carolina are trying to include some part of this multi-quasiparticle coupling in terms of the quasiparticle formats. So it's in QRPA, this in coupling to the collaboration. So in the QRPA, we have proton and neutron quasiparticles, but now they are coupled to one phonon states. This phonon is completely by another QRPA, that particle QRPA. Then this will include the description giant resonance. This is a Lamptera minus function for cell-82, and it's the standard QRPA. Its strength is concentrated into some region, and it is because we are lacking some of the coupling to these complicated states. But by including this quasiparticle vibration coupling, we have a much better handling this experimental data. And here's a comparison with some strengths and arguments. So this will not include all the coupling, but some of the important coupling is included at the QRPA states. And here's the impact to the data decay. So this calculation is actually done without isoscalar appearance. This means the isoscalar appearance basically increase the data decay. So without isoscalar appearance, we have a much larger upright compared to this one. But by including this quasiparticle vibration coupling, there will be some concentration in the lower energy state. So upright is reduced very much. So this effect of this having this coupling is very similar to having isoscalar appearance correlation. This means in future we like to do optimization of the functional, including this coupling. Then probably we will have a bigger isoscalar appearance for some of the effect that we are including in the as isoscalar appearance correlation maybe coming from this kind of particle vibration coupling. So this there will be a big flashing up, yeah. So this the discussion that is here. And a bit about the navigated decay. So we have this proton-neutron pairing 50 standard to data decay half-life. So we can calculate 3 double data decay matrix element. And this kind of calculation was not done before because people are usually interested in neutrino double data decay, but we don't know the strength of that scale again. So people use this neutrino double data decay to fit the strength of that scale again, then discuss the neutrino double data decay matrix element. But now we have a functional to data decay single data. So we can do a systematic calculation. So this is the comparison when you need to in the matrix element for with the experiment. So it's 11 cases where the experimental region. We see some application in the right system, but we have a different media system. Like we are using defined theoretical some approximation and 10 functionals, but basically defined functional is here. We even have some prediction. These are 27 nuclei possible cases of neutrino and zero neutrino replicated for Q value. And again, we like to have some variation by changing the parameters, but for the heavier system, we have a and actually, there's a new experiment called Katsu experiment started by from this calculation. So this is a gadolinium 160, and we get this amount of matrix. And this was actually over 5 times larger than the previous calculation. So previously, the expected half-life was 10 to the 21st year, but with this new matrix element, it is 10 to 20. And the measurement was done 20 years ago in Ukraine, and the lower limit of the half-life is 10 to 90 year. So now the difference between the expected half-life and the measured lower limit is just 1 order. So by improving this experiment by having more isotopes and including the background, we may be able to observe this 2 neutrino. Okay. And this is the experiment, and it will start. It is already funded, and it will start from this year. And yeah, I'd like to discuss a little bit about the auto system. And we usually do not discuss auto system in PFT because it is difficult to handle. Because we have to break time universal symmetry. There are some blocking stuff, and it's really complicated. now we have neutron-proton here. If I construct some states with finite neutron-proton pair condensation by putting some constraint, then this neutron-proton pair condensed state contains odd particle numbers, which compose of 1 neutron and 1 proton. So you have like 3 neutrons, 3 proton states, 5 neutron, 5 proton states. So by performing a proper particle number approach, odd numbers, we can construct some basic states for all the particle numbers. Just doing some easy calculation with this neutron proton. So we can do some GCM calculation for all those approach. And we first try to solve this way solver model, and we get basically perfect agreement with the exact diagonalization for the spin 0 state, spin 1 state as a function of defined interaction strengths. And we also discussed the spin N1 transition between S equal 1 and S 0 states, and their agreement is also perfect. So this framework basically works very well for describing all those systems. And we are trying to extend this discussion to N1 transition probably 18, that is N equals 9 system. And actually, some of the quantity depends solely on the strength of the isoscalar again. So this may be useful to determine isoscalar again. So this is the energy difference between 1 plus state and 0 plus state. And it is related to the strengths. We are also expecting some relation for the N1 transition strengths, but so spin part of the N1 have a correlation with the isoscalar strengths, but there's a post orbital part of N1, and there's an interference part of orbital and spin part, and they actually cancel this contribution, and the total N1 is basically very product as a function of the isoscalar strengths. Yeah, so the energy is pretty expensive, but N1 transition doesn't much. But we may be able to do some of the auto quantities to fit with the isoscalar. Just a little bit. I have to introduce about some new technique we are developing here at NSL, also nuclear PA. So in many of my project, we need to target low energy purity solution. We need to have eigenvalues of eigenvectors. For example, computing tissue inertial calculation for data decay, quasiparticle values coupling, form information, and also target decay. And the standard solution for this QRPA is matrix diagonalization. It's a very large matrix with 1 million dimensions. We do not solve this matrix diagonalization directly, but we basically solve finite amplitude method. It's basically similar, the same method, but we solve this equation in finite way. Now we have a parameter, complex parameter omega, and some external in the right hand side. And we are solving this system as a function of omega. And here still we have some matrix, but all we need is this ax plus by, or b star x plus a star y. And this is a vector quantity. And in the finite amplitude method, this vector quantity is given as a function of x and y. This means that we can solve this linear equation iteratively by starting some initial place from x and y. Then using this solution, we can do a counter integration to extract the original eigenvectors by this integration over the energy. But for performing this counter integration, we need to identify the set. We have to set a counter. So we have to do some strengths. We have to set the strengths and identify where the form. Then we can do this calculation to extract to QRPA eigenvectors and eigenvectors. Now we are trying to reduce basis method. So original idea basically we try to emulate the found x and y amplitude as a function of omega by a set of some training amplitude. So we choose some omega k, and we try to express the arbitrary x and y of the arbitrary value of omega by supposing this solution. But actually, the linear equations constructed by these the assumptions I combined to the so-called QBI equation for generator volume method. So this actually end up is the GCN for QRP by using the farm amplitude X and Y as a basis. So we can have a we can directly have a volume information. Here's a S calculation. You can say the 11 farm basis. We can basically so farm basis are taken in the low energy region from 0 to 10 eV. We get basically perfect agreement for the energy and also very good agreement. So we have just 11, but we can include this smaller 11. There's a 12 states. This is because X and Y have complex quantities. We have for X and Y, you have X, Y star, X star, Y. So in total, we have 44 basis states. We can express more in this small number of bases. So this will maybe this will speed up for any applications in this energy program. So yeah, I'd like to summarize that. So in this organization, discuss about nuclear dynamics in the channel, and in the standard channel, I discuss about pairing of inertia and output ratio, some connection with alpha nuclear combustion. And I also discussed about triplet, and the impact of pairing functions in the decay and the decay and a new technique to speed up calculation. Thank you very much.
You have covered a lot of topics here, and you have made a lot of papers here. Any questions?
Yeah. Okay. So, yeah, very interesting stuff. About the superfluidity in neutron system. So when I think of superfluidity, I think of things like the pairing gap. I think of superfluid condensate fraction, things like that. How do I connect sort of macroscopic systems, big systems where we use superfluidity to what you said about condensation or no condensation? I didn't understand how to make that connection.
Yeah, so we are discussing finite system. We don't have this phase transition in terms of macroscopic system. But the DFT treatment is basically have the same structure. So using DFT, we can define some of the parameter. And we can say condensation correspond to some finite value that I can put in microscope.
But there's something with the double derivative of the two particle separation, right? You're looking for non-zero double derivative. You have four particle removal, two particle removal. So this is somehow correlated with condensation.
So condensation should create this PID. So it should be a 1 Newton.
This is straightforward. But I didn't quite understand this pairing rotation moment of inertia thing where you took the double derivative of the two cross separation energy, right? This was somehow related to condensation. So
it's related only to, but I think this is very special only to finite.
only finite.
Because only small.
Thank you.
Nobuo, you saw those results for beta decay with symmetry pairing experimentally. I mean, the results with the pairing showed very nicely lower lifetime. So yes, it is this one here. Okay, but this PN fund, which gives you very long lifetimes. Wasn't there still some GPD?
No,
this is without energy.
This in QRP calculation.
Yes.
Without
Yeah, but for many years, we know that this is important.
Yes.
For beta decay. So every calculation which does QRP and beta decay uses actually some effective value of GPD parameter.
So this will be, I think, the functional fitted using QRPA, but if we include some beyond QRPA effect and try to fit the functional, again, maybe we will get smaller observation from proton neutron material. Maybe the strength and part of the decay will be directly coming from some.
Okay, so what you say that there is some interplay between GPP and quasi-particle vibration.
No questions.
Sorry for worrying. So I'm curious about your claim the alpha particle having scale having. Do you think there exists some competition between the alpha particle and the different scale?
Well, I don't know.
For example, if in your calculation, if you can extract the information of the neutron scale, can you get some the slope as an increasing of the particle of neutron number, the alpha fraction is going down and the neutron scale going up.
Yeah, then the discussion about it's about the low neutron density situation. Kita discussing how many alpha particles will be there in the low density region, but I don't quite know.
Just a very quick note here. And notice that here, it's actually equal.
Some in mind.
Doesn't actually just keep going down. Actually increase. Okay. Late. So thank you for being here. I just want to let you know, speaker here, they'll be here, right? Still busy here until October. Okay. So if you want to talk on this topic, want to talk to you, just go to the office. The office is near our famous Palos office. You can find it. Thank you.